Hello, ladies and gentlemen. So welcome. We're going to finish off Chapter 8, Forms of a Quadratic. So you were given this on your last day in class, which was Wednesday. Let's take a look at working through some of this. A quadratic can be represented by a graph in the form y equals ax squared plus bx plus c. And equals 0 should not be there. Let's get rid of that. So it can be of this form. The equation of a graph of a quadratic relation can be used to solve different problems. And so that's what we're going to do. We're actually going to do some word problems with this math and figure out what it can be used to help us with. The path of a ball was thrown in the air and modeled by this graph. So this is a ball being thrown in the air. The y values represent the height of the balls in meters. So this is the height as the ball goes up in the air. And the x values represent the horizontal distance that the ball is from where it's been thrown. So what's happening is, if I was to draw a picture of what's going on here, I think what's happening is a ball is being thrown. So here's the ball, and it's going to go over a distance this way. And as it's thrown, the ball is going to go up, and then it's going to come back down. And this is going to be your height above the ground. So we've got a ball, it's being thrown, it's going up, 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 and then it's coming back down. And this is the path of the ball. And this is what we're demonstrating here. This is the path of the ball right here. So, what was the maximum height the ball reached? Well, if we think about what's happening with the ball, this is the maximum height that's the ball is going to reach, right? So it's right up here at what we call the vertex. And that vertex is going to be given by 10 in the horizontal axis. So it's 10 meters this way. And the vertical axis is 9 meters. So the maximum height for this ball is going to be 9 meters. And that's right here. And again, that's at the vertex, right? So how far had the ball traveled horizontally to reach this maximum height? Well, if we come over to the maximum height and down, that's called interpolation. So we come over and we come down, we find that it had traveled 10 meters to reach the maximum height. What horizontal distance did the ball travel before it hit the ground? So there's a different question. So now we want to know how far did it go before it hit the ground. Well, remember, this is the height above the ground. So this would represent ground level, right? 0 height above the ground would be ground level right here. So I guess it's traveled 20, 22, so 21 meters would be the answer. And notice that this distance, when it hits the ground, it hits the ground when the vertical axis, right? When the vertical axis, y equals 0. So it's hitting the ground when y equals 0 here, right there. And we know that we talk about that as the x-axis at times, right? Or the x-intercept, sorry. From what height was the ball thrown? Well, you saw my diagram here. I started here with the person holding the ball because I noticed that in our diagram, we're starting not at 0, right? So the ball didn't start on the ground. That might happen in golf or something where you hit the ball from the ground and it goes up. But at this point, this was your initial height. So that's your initial height. And that happens when the time is, or the horizontal distance is 0. So that's your starting height. So the starting height for this seems to be about 1.5 meters. And that comes from right here. From what height was the ball thrown? And so if this occurs when x equals 0. So notice that this occurs when y equals 0. That means that this is actually, the top one is an x-intercept. And the bottom one, since it occurs when x equals 0, this is actually a y-intercept. And that's where it crosses both of those axes. What is the height of the ball after traveling a horizontal distance of 6? So again, this is interpolation. So you want to go a horizontal distance of 6. So you're going to come across here to 6. So when x, so what's this really asking you? What is the y value when x equals 6? That's what that question's really asking. So when I come out to 6 in the x, I use interpolation to come up to the graph, and I come across, and I find out that it is approximately 8 meters. So when it travels 6 meters from the person who's throwing it, it's about 8 meters in the air. So on my diagram, it would be right about there. And the last question for this one is, what is the horizontal distance when the ball is at a height of 4 meters? And what this is really asking is, what is the x value when y equals 4? And again, that's interpolation because it's within the data that I have here on the graph. So I go to y equals 4 this time. I come across until I hit the graph, and then I come down, and it's approximately 18 meters. And that's the answer for that one. So there you go. Let's flip over and do example 2. The quadratic relation, h equals negative 5x squared plus 210, describes the path of a rock that falls from the top of a cliff. So it's falling from the top of a cliff, with h represents the height in meters and t representing the time. Now this one's a little bit different. What's happening is we have a cliff, okay, and we have a rock that's being dropped from the top of the cliff, and the rock is falling. Now, because of gravity, gravity is 9.8 meters per second squared. This rock actually speeds up as it falls. And because the gravity is causing it to speed up, it has an acceleration. So what's happening is if you were to graph this on a distance time graph, you would find out that the rock, given the amount of time that it is in the air, the time that it's allowed to fall, is actually going to speed up. And it's going to fall something like that. And that will be the path of the ball, and the speed is going to speed up. So the distance above the ground is actually going to zoom. We're going to hit the ground at a faster speed. Now, to be honest with you, there's another side of the parabola. The math comes over on the other side here, and the parabola keeps going. But the path of the rock is just there. We're only going to deal with this one because on this side of the timeline was before we dropped the rock, and that doesn't make sense in terms of the rock, but it does make sense in terms of the parabola. The parabola itself, given by this equation, is the whole thing. This is the whole parabola, but we're only interested in this part of the parabola because this part is negative time, and that's before we drop the rock, and it just doesn't make sense. So let's go back here. Here is the equation. H equals negative 5 t squared plus 210. They want to know at what height was the rock dropped. Well, the initial height occurs when we first drop the rock. So that's going to occur when t equals 0. That's the initial height. That's when I first dropped the rock. So I'm going to put in 0 for t, and you're going to find out that it's 210 meters. So in other words, this top area right here on my graph that I've sort of put in here, this is 210, and the time equals 0. So that point is 0, 210. And that, again, is your y-intercept, isn't it? That's where it's crossing the x-axis. That's our initial height. Find the height of the rock after 4 seconds. Well, in this example, they didn't give me a diagram, a graph where I could come across to 4 and go up and in. I can't use interpolation on this one. I have to use algebra. So what this is saying is, what is the h value when time equals 4. That's what they're really asking. So they give you this equation, h equals negative 5t squared plus 210, and they want you to figure it out when t is 4. So they want you to put in the numerical value of 4 in for t. So it's going to be 4 squared plus 210. Now you have to use order of operations here. So 4 squared is 16, and 16 times 5 negative is negative 80. So that's going to be 130. So what we find out is that when the time is 4 seconds, the height above the ground is 130 meters, which means that if we did have a graph and I came out to 4, I would go up here, that would be 130. We don't have a graph, we had to do it using algebra this time. Here's the question, is the rock still in the air after 7 seconds? Well, that's a good question. So the question is, where does it hit the ground is really what they're asking. And if 7 seconds is outside of when it hits the ground, or is 7 seconds before it hits the ground? So if it hits the ground at 7 seconds, if it hits the ground at 7 seconds, then h of 7, when I put 7 in for t, will be 0. That should just make sense. So, this gives you the height of the rock for different values of t. So if rock is on the ground, then what's going to happen is h of t will equal 0. Now, what happens if 7 is after it hits the ground? Well, according to my math, the parabola keeps going. So I would come out and come down here, and I would hit the parabola at a negative number. So if 7 is after I hit the ground, and I put in h of 7, I'm going to get a negative number. And if 7 is before it hits the ground, I'm going to get a positive value. So it all depends on whether or not I'm going to get a positive or negative value when I put in h of t equals 7. So let's find out. When t equals 7, h of 7 equals negative 5, 7 squared plus 210. You have to use order of operations, so 7 squared is 49. And we end up with a negative answer. Now it's impossible, it's impossible for the rock to go negative at ground level, unless there's a hole or another cliff or something. But we're assuming that this negative means that the rock is on the ground and has been on the ground for a little bit of time. So no, the rock is not still in the air. Because this is negative, it can't still be in the air. If it was still in the air, then this answer I get would be positive because it would be above the x-axis. So since h of 7 is not positive, therefore the rock is not still falling at t equals 7. So no, it's not still in the air at t equals 7. It's hit the ground, and it's probably just sitting there on the ground, not doing much of anything. Okay, that's the end of 8.1. We'll stop there. I'll give you a little bit of work, and we'll come back with the next one.